this is a general introduction to some network fundamentals. So I'll have a look at some basic terms that we might use later on, some topologies for our networks, some wide area network topologies, wireless networks, and then some other terms. Okay, so let's look at some of the terms that we might be using later on in these series of lectures. Well, what we have is we have a user, and the user normally uses a host device. So the host device could be any electronic device that's capable of connecting to the internet. It could be a PC, an Apple, Mac, a mobile phone, or a PDA. And normally that user wants to contact another user, and they will use a network connection. Computers themselves only understand binary information, so when information is transmitted from one host to another, we typically see a binary stream of ones and zeros. This is known as a bit stream. The actual measurement of the potential of passing bits through the transmission connection is typically defined as the network bandwidth, and it's the number of bits that we can send for each second, or bits per second. Computers also use bytes, and these bytes are made up of 8 bits. So often we will define a connection in terms of both bits per second and bytes per second. So bits per second gives the number of bits, and bytes we divide by 8 to get the number of bytes per second. So the network bandwidth gives the potential of a connection for the number of bits per second, but this connection could be shared or could have other efficiency issues. Thus we define another term of the actual throughput, and the actual throughput is the actual rate that a user can transmit to another user at any given time over the connection. So we might have a 1 million bits per second connection, but the actual throughput is only half of that, defined as 500 kilobits per second. So the actual throughput is normally the measurement that we would make to understand the quality of the connection. There are 3 main ways that 2 hosts can communicate. One is simplex, where we only get data flowing in one direction, from this host to that host. With duplex, we can have a connection either way, but only one at a time. So this host could transmit data, then stop, and then this host would transmit data. In full duplex, both hosts can communicate at the same time in either direction. So let's look at our connection. So we have a user who is using an application, and we typically organize our applications in terms of the application protocol that we use. So if Bob wanted to transmit files, he might use the FTP application protocol. If he wanted to make a remote connection to Alice, then he might use the Telnet application protocol, or he might want to use a web connection, so he would use the HTTP application protocol. So how do we get this information from one machine to the next over our network connection? Well, we need some standard way for the machines to be able to, the host to communicate. This might be a Windows machine, this might be an Apple Mac, and this might even be a mobile phone. So as we have so many different types of equipment that we might use, we need some standard way to be able to find them and to be able to reorganize the data on the other side. So the protocol we typically use, or the protocols we typically use, are TCP and IP. and in this series lectures we'll look at these in more detail. But basically IP is the protocol which is used to actually find the data, and TCP is the one that is used to stream, to organize different data streams into a single stream and then reorganize them back into their original streams. So then we need some equipment to be able to communicate with the either end, and for this we might use a switch, a router, firewall, or an intrusion detection system. So we get the concept of network devices. And eventually we need some conduit to be able to transmit the data. So in the end we end up with some form of cables or some sort of communication media, such as the airwaves in wireless communications. And we might need some method to be able to test that all this is working, and we use protocols such as ICMP. So an example network might be this. We have Bob and Alice over here. We have firewalls in between. We have a public channel of the internet. We might have some security devices such as intrusion detection systems throughout. We might have some servers, each connected to a switch, and we can have routers in between. Some of the icons that we might see as part of the Cisco part: a Cisco switch, a Cisco firewall, a network address translation device, Cisco PIX ASA, and an intrusion detection system. Now let's look at some topologies that we might have for our networks. So in this case we have some nodes A, B, C, D, E and F. And before networks came along, these machines tended to be standalone machines. And then the concept of machines intercommunicating came along, and the first logical way to connect the machines was with a point-to-point. So if A wants to connect to B, then we just create a connection between E to F, and then C to D, and so on. So I have the concept of a point-to-point connection. And this is a fairly efficient method, because all the traffic from A that goes to B goes through this media here, and there is no contention, and all the connections can communicate at the same time without affecting each other connection. It's also fairly secure in that the communications between A and B only go between them, so that E and F and C and D can't actually listen to their communications. Unfortunately, this isn't a scalable technology. If E wants to talk to A now, and F wants to talk to D, and F to B, and so on, then the number of connections that we have increases greatly. So we increase the cost of cabling, and it is also not scalable. It becomes extremely complex to be able to route between the hosts. So the next two types of topologies that came along were bus and ring. And bus allowed us to create a shared connection called the bus, and then each host then connects into the bus. So when a node wishes to transmit, it sends its communications along the bus, and then they propagate, and in this case C will pick up the communications from A. The advantages of it is it's fairly simple to cable. We have a new computer that we want to add. We basically just create a T piece and then run the cable, and then we can actually connect to the new machine. So it's easy to connect and disconnect. We can easily disconnect a node from the network, and it will still operate. Unfortunately, it's a shared media, so that nodes must contend to get access to the network at any time. So when the network becomes busy, there is a great deal of contention. Also, only one node can communicate at a time, and as we'll see, we get the concept of a collision, where two nodes try to communicate at the same time and the transmissions crash. The other type of topology that was typical in the early days of networking was a ring topology. With this we create a ring around the network, and we often have two connections, one for incoming and one for outgoing. And the advantage with this is if we use something like a token passing method, so what we do is we pass a token from one node to the next, and if a node wishes to transmit, they keep the token and then they can transmit their data through the network, and then when that's complete they then pass the token on to the next network. If they want to transmit, then they keep the token and transmit their data. In this way we get a fair and honest sharing on the network. Also priority can be given where a token can be kept for a longer time, so that several or many data frames can be transmitted. Unfortunately, a fault on the ring can cause the whole ring to fail. Often what we see is actually two rings, so that if one ring fails, then the other ring can still be used. But unfortunately we end up with four connections in that case. Another problem with this is that often it's a cable which is broken, and if the two rings are in the same cable, then both rings will actually be broken. Often it is also difficult to debug and to find out where the actual fault is, because none of the nodes will actually work on the network. With this one, we can see here that A and B might be working, C might not get any network connection, so the fault was likely to be somewhere between B and C. On the ring network, none of the nodes will actually operate. More modern architectures are based around a star architecture. With this we have nodes which communicate with a central switching or routing device. So if A wants to speak to B, then the data is sent to the central node and then off to B. C to D, send to there and to there. The advantage with this is that these connections can be fairly low in terms of bandwidth, but the major problem is that this is a single point of failure. Also, it needs to be able to switch the data packets fairly quickly. So the performance is very much dependent upon the central switch, but we can get multiple connections at any given time. So A and B can communicate at the same time as C to D. There's also no contention on the network. Along with this, the network bandwidth throughput is actually increased. The bandwidth might be 10 megabits per second on each link, but if both nodes communicate at the same time, then the actual throughput is 20 megabits per second. So we see this type of topology now with network switches, where nodes connect into a switch and the connections are switched inside it. And then we get the concept of a mesh network, and with this we get multiple. This overcomes the problem of the switch, where if one node fails, then we do not get a connection from one node to another. With this we have alternative connections, so if A wants to speak to B, then it might go via this. If this node fails, then it can take a direct route between A and B. So this allows for failover in any of the connections. Unfortunately, all the connections aren't actually here inside the partial mesh, so we can end up with a full mesh where every single node connects to every other node. So you can see here that each node has 4 connections to each of the other 4 nodes. The advantages with this type of topology is that it's resistant to faults in any of the connections, and also gives an optimal usage. The bandwidth between this node and this node can be optimized purely for the communications between them. Unfortunately, it's costly in terms of cabling. It's also complex to be able to organize the network, especially for where the nodes should send their communications. In this case there's only 4 connections, but there might be many more. Every node that we add, we need to add a new connection from the node. it's also difficult to manage the security. If we had any security problems, then it would be very difficult for us to make sure that all the connections were secure. So for LAN technologies, the most common LAN technology that we use is Ethernet. And standard Ethernet uses a technique called Carrier Sense Multiple Access Collision Detection, or CCNA/CD. And with this we use a coaxial cable in which the nodes connect to a shared bus. So each of the nodes listens to the network to see if there's any communications at any given time. So let's say that A and C want to transmit. They listen and they do not hear any communications. But unfortunately they transmit at the same time. So their transmission is sent along the cable, and then eventually the signals will collide and cause a collision between them. A and C will be able to detect this eventually. The signals will move along at some factor related to the speed of light, and they'll be able to detect that there has been a collision. What they then do is transmit a jamming signal for the whole of the network so that no other node will actually communicate at this time. So all A and B both back off their communications and wait for a random time. Once they have waited for that random time, then one node will be able to get access to the network before the other one and to be able to transmit. So in this case we have contention in the network. And standard Ethernet typically uses two types of cable. We have a thin coaxial cable with 10 base 2, or the thicker coaxial cable with 10 base 5. We get a range of about 185 meters with the thin coaxial and 500 meters with the thick. Both transmit at 10 megabits per second. So rather than running a cable, we have a convenient device that we can connect to called a hub. And inside the hub we have basically a bus behind it, which is the same as running our coaxial cable. So we still have collisions and we still have contention with inside a hub. A switch is a more modern device where there is no concept of the bus, and that connections can be switched between one node and another at the same time. So A and C can communicate at the same time as A and C in this case. So there is no contention in this type of network, and there are no collisions. So some of the networks that we see here, we now typically use unshielded or shielded twisted pair cable and connect to a hub or a switch. So we have 10 base T, which gives us about 100 meters for unshielded twisted pair. We can then have the 802.3U standard, which gives us 100 megabits per second. And now we have moved on to 1 gigabit per second Ethernet. So let's look at WAN, wide area connections. So for our local area connections, we typically use technologies such as Ethernet to be able to connect and to be able to intercommunicate. For remote connections, we might use wireless, a dial-up connection, or ISDN. Then we need some form of glue to be able to glue these connections together. So we often use a wide area network connection. This could be in the form of a leased line, where we get technologies such as HDLC, point-to-point communication, or SLIP. We might use the traditional telephone network using circuit switch techniques such as ISDN, or broadband ISDN using T1E1 streams. We might have packet switch technology, where we get techniques such as frame relay, or switch networks, where we take large data frames and split them, chop them into little cells. This type of technology includes ATM